Can you tell what this is on the lower right? It's Noah's Ark. And today we will be talking about arcs and chords. So triangles created by congruent central angles. We're taking a look at that. So what we have is a circle, and there's the central angle EAD, and there's also a central angle CAB. Both of these angles are already marked congruent. So what can we tell? Well, since all radii are congruent for the circle, then we can mark the segments congruent in the triangle. Well, that means that a triangle ADE is congruent to triangle ACB. I could have done ABC, but it still work either way. So basically, these are both isosceles triangles, and why are they congruent? Well, it's side, angle, side. So why would BC then be congruent to DE? Well, they're corresponding parts of congruent triangles, and that makes them congruent. So since the triangles created by congruent central angles are congruent, then the chords created by those angles are always congruent. So these pieces right here, DE or ED and BC, will be congruent as long as those two angles are congruent. The converse is also true, that congruent chords, so if I knew this was congruent to that, that means then the angles are congruent and also the arcs are congruent. So in this example, we have circle A, and it says that BC is 3z minus 6 and DE is 2z plus 6. I want to find the length of BC. Since both of the central angles here are marked congruent, we know automatically that both chords are congruent. So I can set both of those measures equal to each other. So 3z minus 6 equals 2z plus 6. Subtract 2z from both sides and then add 6 to both sides, and I get z equals 12. Then I can substitute that back in for a z, and I find out that BC is 30. So if BC is 30, ED is also 30. Arc measures, just the measure of a minor arc is equal to the measure of its central angle. So that's one thing we know. And also the other thing you want to keep into account is that all of the central angles will sum to 360. So how will we use that? A lot of times you'll see a circle, and it might have some lines going through the center, creating different angles. And you'd be expected to find the measures of all those angles. Well, first of all, these are arcs right here. You can see the little curved line on top of them. And we're going to find their measures. So first of all, I know the measure of arc CE equals 56 degrees. I should have the degrees there. Then, since these are vertical angles, arc BF is also 56 degrees. So those two are congruent. Arc DE, because this is a 90-degree angle, is 90 degrees. Then I can find arc DB, I'm going to call it X, and say this plus 56 has to equal 90. Now I could have done X plus 90 plus 56 equals 180, and that would have worked just fine. But I also know that when I take the 90 out of the 180, I'm left with 90. So subtracting 56 from both sides, I get 34 degrees. So this arc is 34 degrees. Now I'm going to find Y. Well, this makes a linear pair with the 56 degrees. So Y plus 56 is 180. Subtract 56 from both sides. So this angle is 124 degrees, which means this arc CF is 124. And since that's the vertical angle to EB, that is also 124. So we found all the arc measures. Oftentimes with this kind of problem, you'll see the degrees written on the edge of the circle when they're referring to the arc measure. So reflecting on this part of the notes, what two segments form a central angle? Hopefully you remember it's two radii. Why are triangles created by congruent central angles always congruent? So anytime I have two congruent angles coming from the center, we know that the triangles will be congruent. If two different size circles have congruent central angles, do you think the chords will be congruent? What about the radius? I'll let you think about that one and we can discuss in class. What is the relationship between the central angle and the arc? Hopefully you'll know that they have the same measure.